Alright, here we go. We got a new unit here, Unit 2. We're going to start getting into reasoning and proof in this unit. So the first thing we're going to do, we got inductive reasoning. Alright, so we are looking for patterns. Alright, now you might want to take a second to pause the video, kind of get some of the vocab down. This is the same, definitions that are on the notes that are online here. So anyways, you got a second to pause, and here we go. Now you got inductive reasoning. You got that is a process that includes looking for patterns. That's the key thing. Whoa, what's going on here? That's the key thing for inductive reasoning. Tomorrow we're going to get into deductive reasoning, which is a different type of reasoning. But this one here, we're looking for patterns, and we're going to make these things called conjecture. So conjecture is a conclusion. That's a big thing you want to realize there. So a conclusion, and that's based off of inductive reasoning, or based off of looking for patterns there. All right. Now we also get into this thing here called a blank is a specific case for which a conjecture is false. We call this a counterexample. And counterexamples, you only need one of them to prove a statement false or prove it not always true. So you only need one. Now, there's a lot of counterexamples to statements. Usually there's not going to be just one. Usually you can come up with many different ones there. So while we are representing each type of reasoning separately, each is never used in isolation. Both types of reasonings are applied together to reach conclusions that are related to logical reasoning. And once again, you're going to get into the deductive reasoning tomorrow. Okay. Anyways, use inductive reasoning or use patterns, once again, to complete the patterns below. It's kind of weird to say there, but anyway, so this first one here, you got 2, 4, 6, 8. And what I'm noticing right away is it looks like we're going with even numbers here, so I'm going to use that pattern to figure out what the next few numbers would be. So you'd go 10, you would go 12, and you'd go 14. All right, now some of you guys might think differently. Some of y'all might say these are even numbers. Some of you guys might say you're just adding 2 every single time. All right, so either one of those right there would probably be good. Now this next one is a little weird here. You got 1, and then you got 2, and then you got 4, and then you got 5, and then you got 10, and then you got 11, and then you got 22. So this one's a little bit more obscure here. It looks like from each of these here that I have highlighted, they're adding 1 to each of those numbers there, the first number of each one that's highlighted there or underlined. And then you're going from this 2 to 4, and then you're going from 5 to 10, and then you go from 11 to 22. So it's, to me, this is maybe one of these weird patterns where the next thing I'm going to do is I'm going to add 1, it looks like. And then after that, I think it looks like we're going to multiply by 2. So I think the next number here, you'd go 23, and then I guess multiply that there by 2, so I think you get 46, and then add 1 again, so 47, and then I guess multiply by 2 and keep going. That one's kind of a weirder pattern. The next one here, let's look at this. So let's see, you got 1, and then you got 1 over 8, and then you got 1 over 27. So you're getting some weird stuff going on here. First of all, this isn't a fraction, this first number. So what I'm thinking of is maybe it's supposed to be a fraction, but maybe they did something kind of weird. So if I think about it, okay, I could write 1. I can write anything as a fraction by putting it over 1. So now we got that in the fraction format. So we got 1 over 1, we got 1 over 8, we got 1 over 27. And, some people still might get this, some people might not. What I'm seeing here is looking at all of these denominators here. And, I've seen this problem before, so I already kind of know what to look for here. What I'm seeing here that the denominators are perfect cubes. So think about this. What is 1 over 1 squared? Or I'm sorry, not even squared. Let's go cubes like I'm talking about here. 1 cubed. 1 times 1 times 1 is 1. Okay, what if I went, and I'm running out of space, I'm going to go over here. So 1 over 2 cubed right there. And that's, 2 times 2 times 2, that should be 8 there. So that works out so far. Let's double check the last one there. 3 cubed, so 3 times 3 times 3, and that should get us actually 27. So I think this next one here should be 1 over 4, and then, here I'm going to zoom in there, cubed, which I think is the same thing as 1 over 64. So I think that is probably, that kind of looks like our pattern right there. So you can also go 1 over 5 cubed, and that should be 1 over 125. If we continue that pattern, and then I guess the last one there, we'll go 1 over, I guess, 6 cubed, and 6 cubed, that should be 216. And then there you go. That is the final one. I guess that's technically not the answer. All these blanks are the answer, but anyways, kind of a weirder pattern. This one's even weirder because right here you got a bunch of letters instead of numbers. So, all right, let's see what's going on here. So you got OTTFS or FF and then SS, and then people think, okay, it's probably going to be E and then maybe some other obscure letter there, but you got to look kind of closely. This one's kind of tricky here. Trick to this one is think about your numbers. Think about 1, 2, 3, 4, 5, 6, 7, and then 8. Whoops. I guess I should put the number 8 there. But anyways, what I'm noticing with this one here is if I spell them all the way out, look at this. You got 1, 2, 3, and then 4. So notice that each of these here, it looks like you're doing the first letter of each one of those numbers there, which is kind of weird. It's very loosely connected to numbers, but it is still connected. So there's nothing mathematical about it other than the fact that you're just increasing your number by 1, but then you're going with the first letter. So I guess this next one here, 9, starts with an N. 10. I'm probably going to go with the T right there. So that one right there, not as an obvious pattern. So hopefully, we do enough of these so you can see certain patterns. And then hopefully, maybe the ones they'll ask you on a quiz or test will be kind of related. So sometimes they're not mathematical. All right, so let's see here. We got these shapes here. You'll see these every now and then. You got a circle, and then a triangle inside of that. And then after that, you got a circle, triangle, and then another circle going on there. So I think the next one here, so we're going to go circle. Please excuse my sloppy circle. It's kind of hard to do on the iPad. You're going to have a triangle. You're going to have another circle. And then maybe another triangle inside of that. It's just like this spiraling, like this pattern that, keeps shrinking inside of there. So kind of a weird one. You can draw the next one there, but we'll go ahead and continue here. This next one here, let's see, SMTWT. Maybe we see these, more often than those letters up there at the top here. This one's kind of going for like Sunday, Monday. Here, let me do it like this. Sunday, Monday, Tuesday, Wednesday. So obviously Thursday, and then maybe Friday, Saturday. And y'all might have seen that a little bit more often. Sometimes they'll do that on calendars to save space. So usually if we see those together, it's not too bad. What do we got here? Describe how you can sketch the fourth figure in the pattern and sketch the fourth figure. So it looks like here you got 2 blocks, and then the next one you got 4 blocks, and then the next one you got 6 blocks. So I'll bet you that last figure here, we're probably going to have 8. Looks like these are going up by 2 blocks each time. So I'll see if I can get something kind of close to that. And then it looks like one of them is shaded. It looks like the bottom left is always going to be shaded. So I'll go back here and kind of fill in that block right there as best I can. So that kind of looks bad here. Maybe I'll do this. But anyways, there you go. Kind of looking at patterns, looking at shapes there. So that's an example, or those are a few examples of using this inductive reasoning. Remember, we're looking for patterns today. Okay, so let's flip over here. True or false, Candace examined 5 different examples and came up with this conjecture. If any 2 positive numbers are multiplied, then their product is always greater than either of the 2 original numbers. All right. So we want two positive numbers are multiplied, then their product is always greater than. So is she correct? I'm going to say no here on this, because partially I know why, but then at the same time, we're going to come up with this thing called a counterexample. Counterexample for this. So let's see what we got going on here. A counterexample. So I need two numbers that are multiplied, and then their product is always greater than either of the original two numbers. So an example, there's many different ones here. There's not usually only one. So I'll write down a few here. So you got 2 times 1 right there. Those are both positive numbers. When I multiply them together, that gets you 2. 2 is not greater than, so I'm going to put a little line through that. Kind of do it like that. 2 is not greater than 2 right there, because it's saying that it's always greater than either of the two numbers. 2 is not greater than 2, so that would be a counterexample. That one doesn't make sense to you. Here's another one here. I'm going to do fractions here. So the fraction 1/2, that's definitely positive here. So we'll go 1/2 times maybe another 1/2 for kicks. The same number there. 1/2 times 1/2 right there. That's going to get you a 1/4. Okay, 1/4 is definitely not greater than either of those two numbers that we multiplied by in the first place. So those are two different counterexamples there. And that's how you'd write them. You just write something out kind of logically like that. Your teacher should be able to figure out kind of what you're going with there. Okay. Discover the pattern. Use inductive reasoning to find the sum of the first 20 odd numbers. All right, so I guess we're going to use a pattern. Maybe we can figure out kind of what's going on with each of these here. So I guess they say 1 equals, I guess, 1 right here. And then I guess we got 1 plus 3. So that should be 4, right? Then the next 3, you got 1 plus 3 and then plus a 5 there. So take your previous thing, add 5 to it. So okay, so we got 1, 4, and 9. We got 1 plus 3 plus 5, and then add a 7 onto that. I think that should be 16. And then add on a 9, and you got 25. All right. So each one of these steps here, kind of looking for a pattern going on here. Now each step going down here, it's not really an intuitive pattern, but with the numbers themselves, so if you look at them individually here, I notice that these are all perfect squares. So those are all perfect squares. 1 squared is 1. 2 squared is 4. I'm going to squeeze those in right here. 2 squared, 4. 3 squared, 9. 4 squared, 16. 5 squared, 25. So I guess the next one here might need to be 6 squared. You could get 36. And we can also get that by adding the next odd number. So what is that, 11? 11 plus 25 definitely gets you 36. So I think this works out here. So we're going to go with the conjecture being each number of steps you go, you're going to take your n, or the number of steps you've gone, and you're going to square that. So we can use that to help predict what will happen way down the road. So I guess the first 20 odd numbers, so I guess that'll be 20 squared right there. So you know, instead of writing that pattern out 20 times, now we can just say, hey, it's probably going to be 20 squared, which should be 400 once you add those numbers up there. So that's how a conjecture can be used right there to make your life a little bit easier there, or solve, some type of problem like that. So what are we doing here? Example 1, conjecture. The sum of two numbers is always greater than the larger number. Oh, okay, so this is another one of these ones. Come up with a counterexample. Is it true all the time? Is it not? Now they have a spot for counterexample, so it looks like we're probably going to have a counterexample. So the sum of two numbers is always greater than the larger number there. So it doesn't have any criteria on the number. It could be any type of number. So let's see here. Maybe we could do something like this here. Let's try this. Let's try, since it didn't say anything about the numbers, I'm going to try some negative numbers here. So I'll say -2. I'll add on 4 right there. So there's the sum of two numbers there. And that should be greater than both of those numbers, whatever that is. So I think you're going to have 2 there for that answer. So yeah, okay, so 2 is greater than the sum is definitely greater than the negative 2. So I agree with that right here, but I don't think 2 is greater than 4. So that right there does not work out. So this would be a counterexample. This would be something that makes that statement not always true. Remember, there can be multiple counterexamples. That's not, the one and only. You can do multiple of them. Okay. Next one, quadrilaterals with 4 right angles are squares. So we can draw a quadrilateral, a 4-sided figure. Here's one with 4 right angles here, and this is definitely not a square. Based off of the side lengths, it looks like I have here. This right here is a rectangle, right? So there would be a counterexample, just using a shape. So that's really all you can do there on that one. Conjecture, what do we got? Sorry, I was flipping over my hard copy of my notes. What do we got? Supplementary angles are always linear pairs. Right. Now, we kind of talked about this a couple of days ago. This is somewhere in the middle of Unit 1. Supplementary angles. There's actually a theorem that we talked about where supplementary angles don't necessarily always need to be connected. They can be completely detached from one another. So I could take 2 angles like that, completely detached. Maybe I'll call this angle A and angle B right there. So totally detached. But supplementary angles means they add to 180 no matter what. Okay, it doesn't matter if they're side by side or adjacent. So therefore, they don't have to be a linear pair. So that would be an example of a counterexample. So anyways, that's about it there. I guess one more thing that you could go ahead and talk about. Sometimes you'll see this weird thing called a Fibonacci sequence. And I think that comes up on a couple of homework, maybe a homework question. So it's this weird pattern. It's really hard to see at first, but then once you see it, it's not too bad. So Fibonacci sequence, you take 2 numbers here. So like maybe I'll start out at 0 and then I'll put 1. And then what the next number is, you add the 2 previous numbers to get the next number. So you could add 0 and 1, and then I guess that would get you 1 right there. And then you could add 1 and 1. And then that would get you 2. And then you could add 2 and 1, and then I guess that would get you 3. And you could add 2 and 3, and that would get you 5. You could add 3 and 5, you get 8. 5 and 8, you get something like 13. And it's got this weird, pattern to it. And that's kind of a tricky one that you might see pop up there in the homework. So it's called a Fibonacci sequence. A lot of applications actually behind this. It's such an obscure pattern, but you'll see it come up every now and then in some homework questions. You'll see it come up in like these weird like spiral looking things. I've seen it like compared to like a seashell type of thing. So anyways, you can find a bunch of cool stuff on the internet for that. But that is it for our lesson here today. So have a good one.